Hi everyone, welcome to our online class on electricity and electronics. This is Paradise Business and Technology College online class. The class coordinator is Mr. John Kaupa. The duration of the course is 10 to 15 weeks. This course is for all the diploma in trade students and diploma in engineering. They will be taking this course as one of their foundation year course, because electricity and electronics is one of the very important course for them to understand. So in their field, like especially for trade and engineering, they must have a fair bit of understanding of electricity and electronics. So let's look. We have these topics for the course. The first topic is quantities, measurements, and units. For every topic, we have an assignment and we have a quiz each for each of the topics, and the duration is 1 week. It may go beyond 1 week, or it may be conducted less than 1 week. It depends on how fast we can get the course done online. Okay, the second topic is atoms and elements. Third one is conductors, insulators, and semiconductors. Voltage, current, and resistance is the fourth one. The fifth one is Ohm's law, energy and power. And then we have series circuit, parallel circuit, series parallel circuits, magnetism and electromagnetism, properties of alternating current and voltage, resistors, capacitors and inductors, RLC circuits and resonance. RLC stands for resistor, inductor and capacitor circuits. Diodes and application, transistors and application. So basically this online electrical class on electricity and electronics will cover these areas. Our first topic, let's look at physical quantities. Physical quantities are measurable properties of a physical system comprising a numerical magnitude and a unit. Example, 2 kilometer. So 2 is a magnitude and kilometer is the unit of the quantity. So meter is the physical quantity, the unit is kilometer, meter and all this, and the magnitude is 2. So a physical quantity is a measurable property of a physical system comprising a numerical magnitude and a unit. They are fundamental for describing physical laws and are divided into base quantities, like the basic quantities: length, mass, time, current, temperature, amount of substance, luminous intensity, and derived quantities, which are speed, force, anything that is derived from these basic quantities. So the basic quantities are length, mass, time, and all this, temperature, amount of substance, luminous intensity. The derived quantities are derived from these base units. So basically physical quantities can be derived or base quantities. So force, speed, velocity, energy, density, pressure, all these are derived from the basic quantities, primarily using the international system of units. Okay, so there's a difference between basic and physical quantities. Physical quantities, we have two types of physical quantities, like I've explained earlier on. Base quantities, the 7 fundamental independent quantities that form the foundation of physics with SI units: length, meter, mass, time, electric current, temperature in Kelvin, amount of substance, mole, and luminous intensity. So these basic quantities, they have a basic unit, like length is in meter, mass is in kilogram, time in second, electric current in amperes, temperature in Kelvin, amount of substance in mole, and luminous intensity, that's the measure of the brightness of light, is candela. These are all 7 basic quantities. We also have derived quantities. Derived quantities are derived from these base quantities up there. So quantities are defined by combining base quantities through physical laws such as area, velocity, force, density. They are also physical quantities, but they are derived from the base quantities up there. Like for area is length times length, area times width is length times width is length times length. So area is derived from the base unit length. So length is a base unit, area is derived from that base unit or base quantity. Components of a visual quantity. Visual quantities, they have two components. A complete measurement consists of two parts. We have the numerical magnitude, the number that indicates how many of the unit are present, example 10, and unit, the standard used for measurement. So kilograms is the unit, and then the size of the quantity is in terms of number. So 10 kilograms. So 10 is the magnitude, kilogram is the unit of the quantity, and the quantity is the mass. Mass is the quantity, the unit of mass is kilogram, and the magnitude of mass is 10. It can be any magnitude. So components of visual quantities comes in two components. We have the magnitude and the unit, like 10 kilograms. Kilogram is the unit of the quantity, and 10 is the magnitude of the. We also have from all the visual quantities, we have basic electrical quantities. Basic electrical quantities are fundamental parameters used to analyze and design circuits, including voltage, or sometimes they say potential difference, or PD, or sometimes they say electromotive force. Voltage is a force that pushes current, pushes electrons or charge in a circuit. So when there is a movement of charge, or when there is a movement of electrons, there is current. So current is a flow of charge. Resistance is the opposition of flow of current. And then we have power. Power is energy, the rate of use of energy in the circuit. So power is the rate at which electrical energy is consumed in a circuit. And we have charge. Charge is the charge of the electrical quantity. Key units are volts for voltage or electromotive force, amperes for current or amps, ohms for resistance, watts for power, and coulombs C for charge, and it's governed by the famous Ohm's law. Okay, voltage V is represented by V or E, measured in volts. This is the electrical potential difference, or push, or sometimes they say the electromotive force, because voltage is a force that pushes electrons through a circuit, that causes charge to move or electrons to move. Is defined as energy per unit charge. Or another the equation for voltage, you can also use energy and charge to calculate voltage. So if you use Ohm's law, it's V is equals to I times R, current times resistance. But you can also use V is equals to energy divided by charge. Current I measured in amps or amperes, and the symbol is A. This is the rate at which electric charge flow through a boundary, calculated as I is equals to Q on T, or charge on time. So the amount of charge, or the amount of electrons flowing through a circuit, is referred to as the current. Resistance is basically the opposition of the flow of current. It's denoted by R, measured in ohms. This is the opposition to the flow of current, calculated as R is equals to V on I, according to Ohm's law. Power measured in watts. This is the rate at which electrical energy is consumed or produced. P is equals to V times R. So power can be two power. One is the amount of power consumed, and two is the amount of power produced. So later, when we come to loads and generators, we will see that power produced is measured in kilowatt, kVA, and power used is measured in kilowatts or watts. So there's a difference between these two types of power: generated power and load power, the amount of power that is needed to by the electrical load in a circuit. Charge Q, measured in coulombs. This is the base property of matter that causes electrical phenomena, and the equation is Q is equals to IT. Charge is equals to current times time. Energy or work. Energy can be different types of energy, but in the context of electrical, we say electrical energy, or it's basically the work that is done in the circuit. So Sometimes you can say work done in a second, or you can say electrical energy. So it can be work or J for joules. Measured in joules represented, it represents total work done in a second. So energy is equals to power times time. Additional electrical quantities, we have conductance. Conductance is the inverse of resistance. It's denoted by G. G is equals to 1 on R. So conductance is basically the measure of the conductivity of a material. Okay, so the lower the conductance, the higher the resistance. The higher the resistance, the lower the conductivity. So capacitance is one of the electrical component that has a unit, and it's also is a physical quantities. One of the physical quantity is measured in farads, the ability to store charge. So capacitor is one of the second component, and the measure of this second component is measured in the amount of the ability of that component to store charge. So it's measured in farads after Michael Faraday. Inductance measured in henries, the ability to store energy in a magnetic field. So we also have frequency measured in hertz, the number of cycles per second. So frequency, later when you come to different power sources, you will see that we have DC and AC. Frequency comes into play when we talk about AC power, alternating current. So it's one of the electrical quantities that we are going to look at. Okay, these are the different electrical quantities and their units. We have charge, the symbol is Q, unit is coulomb, formula is current times time. Current is I, it's measured in amps, symbol A, it's Q on T, or charge on time. Or if you use Ohm's law, it's current is equals to voltage over resistance. Energy, sometimes it's J or W, is the work done in an electrical circuit. It's measured in joules, J, and the formula is you multiply power with time. Power is P, measured in watts, is the rate of work done in a second. So it's work or energy, electrical energy per time. So there's the formula. Resistance R is measured in ohms. The formula to calculate resistance in an electrical circuit is the voltage in the circuit divided by the current in the circuit. Voltage, symbol is V, it's measured in volts. The formula for voltage is work, electrical work in a second divided by the charge or flow number of charge in a second. Or when you use Ohm's law, it's voltage equals to current times resistance. We have inductance. The symbol of inductance is L. The unit of inductance is Henry, and it's denoted by H. Is equals to inductance over it's equals to mu over current. Okay, mu over current is the amount of magnetic field divided by current in a second. Capacitance is denoted by the symbol C, C for capacitance, and it's measured in farad after Michael Faraday, and it's denoted by F for Faraday. The formula is charge over voltage if you want to calculate the capacitance. Frequency F, it's measured in hertz. Its frequency is also the inverse of time. When you put 1 on T, or when you get the inverse of time, then it's frequency. So frequency is the inverse of time. Impedance Z is measured in ohms. It's also equals to V on I. So impedance is the total resistance of a circuit, including the imaginary component as well included in the circuit. So that's impedance. We also have admittance. Admittance is in ohms. It's also one of the electrical quantities. Is measured in ohms. So that's V on I. We also have conductance, which is the inverse of resistance. This is a this is the Ohm's law, but then we also include in this circle here. It's a very useful circle. You might want to take note of this circle. Draw the circle nicely and write all the formulas here. We have this is the expanded version of the Ohm's law. You can draw this table and see. So how do you use this circle here? You can go to the first quadrant there. You see for volts, volts is equals voltage is equals to power on time. Voltage is also equals to current times resistance, and voltage is also equals to the root of power times resistance. So these are the three formulas that you can use to work out voltage in a circuit. You can also look at the quadrant where it says amps, that's current. So when you see these three formulas there, current is equals to V on R, and current is also equals to power divided by voltage, and current is also equals to root of power over resistance. So this is the expanded version of the Ohm's law, the triangle. You try and copy this one, try to understand this circle here, and then later in one of our example we will see how we can use this circle here. Similarly with the power and resistance, they all have three formulas here. Resistance is equals to voltage over current, resistance is equals to voltage square over power, and resistance is equals to power divided by current squared. So also for power is equals to voltage times current, power is also equals to current squared times resistance, power is equals to V square on R. So these are the different formulas that you can use to work out the circuit parameters: current, voltage, and resistance, and power. Later we need to have more examples on that. You will know. Okay, all the circuit components that we discussed up there, they have a symbol here. So in any electrical circuit, we don't draw the whole thing in there. We don't draw a battery or generator, whatever. Instead we use the symbols. So circuit symbols are very important in the study of electricity and electronics. So instead of drawing all the artistic drawing of all the circuit components, we just use the symbols here. So the first symbol up there is a resistor symbol. Resistor looks similar to inductor, but inductor inductor is different from the resistor. Don't confuse resistor and inductor. We have capacitor, two plates there, you see that, and then we have diode on the other side, that arrow, and then we have a bar there, and then we have a switch there. That switch there is an open switch, and then we have fuse, symbol of fuse. Alternating current, you see that AC sign there and a circle. Direct current is a straight line. So the difference between AC and direct current is just fixed value. It doesn't alternate, but alternating current, they alternate and increase in value, decrease in value, increase in value, decrease in value, from negative to positive. So that's when we have frequency coming in. We have a circle and A in there is a ammeter. Ammeter is a special electrical measuring device that measures the amount of current. Voltmeter used to measure voltage. Wattmeter used to measure power. Watt, W, and a circle. And then that after watt there, you have this ground symbol there, that's grounding. And then we have two coil of wire. There's a transformer symbol. Okay, so up there is single coil there, it's an inductor. If you have two coil facing each other like this, is a transformer symbol. And then circuit breaker. You don't confuse yourself with a circuit breaker and a fuse. They are both protective devices, but they have a different symbol. But they function at the same thing. But they are quite there are some few differences between circuit breaker and fuse. Circuit breaker trips when there is a fault in the circuit. Fuse, they blow when there is a overloading or if there is a fault in the circuit. So that's the difference. Cell symbol there, battery or whatever, and then we have battery there. If you put two or more cells together, you form a battery. So single cell, just cell there. And then we have electric lamp symbol, that circle and the X in there. Electric motor, circle and M. And then we have relay symbol. So relay there. Relay is also one of the protective device, and it's also a controls the flow of current in a circuit as well. So later when we do advanced circuit like control circuits and electronics, we look at the function and how relay works in a circuit. And then electrical line or wire symbol, if there is a straight wire, whatever. Okay, so basically these are the electrical symbol. Electrical quantities and measurements. Let's look at the type of instrument used to measure the different quantities here. Current, its unit is amp. It's measured by amp meter or ammeter. Okay. Voltage measured by voltmeter. Power, watt, power meter, or you can say watt meter. Resistance is measured by ohm meter. Capacitance meter. Inductance meter. Frequency, period. Period and frequency is frequency is the inverse of period or time, and time is the inverse of frequency. So they're inverse of each other. So it's time and frequency inverse of each other. So they are measured by oscilloscope. You can put any alternating current into a oscilloscope, any high frequency signal, and you measure the frequency and the time and all these things. So charge, electric charge, the column, and it can be measured by charge meter, and conductivity meter. So these are the different electrical measuring devices that are used to measure electrical quantities. Like for mass, we use a weighing machine to measure the mass, and it gives us gram or kilogram. For meter, length, we use ruler and tape measure and all these to measure length. Likewise, for all the electrical quantities, they are measuring instruments that they use to measure these quantities. So they are all here, ammeter, voltmeter, and all this. But with the latest technology, we have this only one meter that does all the measurements. They call it multimeter. So multimeter can measure voltage, current, resistance, capacitance, inductance, even frequency, and also temperature and all this. So multimeter can perform everything. Okay, let's look at atoms and elements. When we talk about electricity, let's understand different types of materials. When you want to understand the different types of materials, conductor and insulator and all this, we go back to the type of element that they are made up of and the atomic structure. So this will give us a clear picture of a material, whether it's a conductor or it's an insulator, and how it becomes an insulator, how it's a conductor, or how it's a semiconductor. So conduction of electricity or non-conduction of electricity is determined by the atomic structure and the atom of a single element. So let's look at this one. Atoms are the fundamental building blocks of a matter composed of protons, neutrons, and electrons. So an element, like any element, they have atom. In the atom, we have protons, neutrons, and electrons. An element is a pure substance made of only one type of atom, defined by its specific number of protons, which is the atomic number, and there are 118 known elements organized by this unique atoms in the periodic table. So elements are organized in the periodic table. Let's do it. This is a periodic table. It's an arrangement of all the elements here. Okay, so these elements, they have the smallest building block of these elements are atoms. So when you go down to the atomic level of a element, we have protons, neutrons, and electrons present in each atom of a element. So elements are made up of atoms, and in the atoms we have the protons, neutrons, and electrons. So let's go. Atoms. Okay, let's say atoms. Let's say example carbon. Carbon is an atomic number of a mass number of 12 and atomic number of 6. So when you subtract 12 from 6, we have 6 protons, 6 neutrons, and 6 electrons. So these neutrons, protons, and electrons, they are present in an atom of an element. So it depends on the different types of elements. Different types of elements have different number of protons, neutrons, and electrons. So like for carbon, it has 6 protons, 6 neutrons, and 6 electrons. So when you talk about atoms, let's go further and look at atoms. atoms, they have a nucleus. In the nucleus we have the protons and the neutrons in the nucleus, which is the center of an atom. An atom is an element is made of an atom, and an atom has a center, which is the nucleus. So in the nucleus we have the subatomic particles, the neutrons and the protons, and the electrons orbit the cell of the atom, or orbit the nucleus. So these are subatomic particles. Okay, now let's look the structure of an atom. Like everything else, atom have a few different things floating around inside of them. The subatomic particles include neutrons with no charge. Neutrons does not have any charge and is present in the nucleus. Protons, they are positively charged, but they are present in the nucleus. So protons and neutrons, they are in the nucleus. Electrons, they have a negative charge. So they are present, they orbit the cell of the atom. So these electrons, when they are orbiting the cell of the atom, that's when we apply voltage, these electrons tend to move, because electrons are particle. When you apply force, you can move these electrons. When these electrons move, there's a time we have flow of electricity. So the protons and neutrons are in the atomic nucleus of the atom, while the electrons orbit the atomic nucleus. Think of this as similar to the way the planets all orbit the sun. That's an atom in a nutshell. Well, if a nutshell was orbited by lots of little electrons, that is it. So when you look at the way our solar system is, all the planets, they orbit the sun. The sun is the center of the our solar system. So it's similar with the atomic structure of atoms. The neutrons and the protons are present in the nucleus, and the electrons, they orbit the cell of the atom. So these free electrons are responsible for chemical reaction and also conduction. Okay, these are some structures of common elements. We have chlorine atom, we have chlorine ion, we have sodium atom, and so sodium ion. So an ion is when an element loses or gain an electron, that's when it becomes an ion. So we have chlorine, we have 7 protons and 7 electrons. 7 electrons, they orbit the cell, and 7 protons and 17 protons and 17 neutrons are in the nucleus. And then we have chlorine ion, which is a minus. So when it minus, that means it's gaining 1 electron, so it makes the electrons goes up to 18 electrons. So when you have a minus, that means it's gonna gain an extra electron. When you have a plus, it becomes it's losing electrons. So positive plus ion are called cation, and minus ion are called anion. That's from your chemistry class in grade 12 or grade 11. And then let's look at sodium. Sodium has 11 protons and 11 electrons. The number of protons and neutrons are always equal, but the number of electrons the number of electrons and protons must be equal at all times, because they are both negative and they are opposite charges. So in order to maintain the balance in the atomic structure, the number of protons, which is a positive plus, and the number of electrons, which is a negative plus, must be equal to balance the atom. When there is no balance now, then this atom becomes anion or cation. Okay, electrical conductivity and atomic structure. Electrical conductivity is determined by atomic structure, specifically the presence of free moving delocalized electrons. So the electrons orbiting around the cell of the atom, okay, we have free electrons. They orbit the outermost cell of the atomic structure, or they are also called the valence electrons. They are responsible for conduction of electricity. Okay, So elements with high conductivity like metals like silver, copper, aluminum have low electronegativity and loosely held valence electrons. Conversely, non-metals like sulfur hold electrons tightly, resulting in low conductivity, while insulators often have filled electron cell. So insulators, the electronic configuration of insulators is fixed, while for conductors we have a lot of free electrons, and for semiconductors it's in between. So let's look at how the atomic structure and electronic configuration of atoms affect their conductivity. Conductor, it's normally 1 to 3 valence electrons orbiting the outermost cell, and for insulators we have full valence cell, meaning the number of electrons needs to be orbiting around the outermost cell is fixed, like for this case is 8 for the insulator. So 8 is the number of electrons required to orbit the second cell, so we have 8 electrons there. So all insulators, they have fixed electrons orbiting the outermost cell. Semiconductors, 4 valence electrons. So basically the difference between conductor, insulator and semiconductor in terms of their atomic structure: 1 to 3 valence electrons orbiting the outer cell, it should be a conductor. Full valence electrons valence cell, then it's an insulator. And if there are 4 valence electrons around the outermost cell, then that material is a semiconductor. So like silver and all this, they are conductor. Germanium and silicon, semiconductor. And we have other non-metals, they are all insulators. Okay, let's look at the difference between conductors, insulators, and should be semiconductors. Up there it's not the spelling there is not correct. It should be SEMI, conductors. Anyway, conductors, insulators and semiconductors are classified by their ability to pass electricity, defined by their atomic band structure. Conductors allow easy electron flow, insulators block it, and semiconductors can control it based on temperature or doping, forming the basis of modern electronics. So basically semiconductors, sometimes they conduct electricity, sometimes they don't. So because of this reason, most of the semiconductor material are used in control sector, control like control like transistor, diode and all this. The ability to conduct electricity will be affected by the temperature and sometimes the voltage level that we apply. The higher the voltage we apply to a semiconductor, it will change the semiconductor into a conductor. If we increase the temperature, the semiconductor will turn into a conductor. If we decrease the temperature, that semiconductor will turn into an insulator. So insulators, they totally block off, or they don't allow flow of current or charges. Conductors, they allow flow of electricity or electron or charges. So these are the different metals here: gold, silver, copper, iron, aluminum, etc. They are all conductors. Silicon, germanium, selenium, gallium, arsenide, etc. They are all semiconductors. Glass, rubber, oil, plastic, diamond, etc. They are insulators. They don't allow electricity to flow. So semiconductor, they can be an insulator or they can be a conductor at sometimes, depending on the level of voltage that we apply to that material, or increasing or decreasing of the temperature. So sometimes there is one process that they go through, especially in the modern electronics. They use that method, doping. They add impurity to the semiconductor to change its electrical conductivity. So doping is a process that they add electrical impurity to electrical as semiconductors to increase or decrease their conductivity. Okay, so these are the different voltage, current, and resistance. Voltage, current, and resistance are fundamental electrical concepts linked by Ohm's law. V is equals to I. Voltage is the potential difference or push, or you can say force. Current, I is the flow rate of charge, is measured in amps, and resistance R is the opposite to that flow, is measured in ohms. Increased voltage boosts current, while higher resistance decreases current. So if you increase the voltage, that means you are increasing the force that pushes the current and electrons through a circuit. But if you increase the resistance, that means you are increasing the resistance of the circuit, so that there will be less current to flow through. You are resisting the charge or the electrons to flow through. So current is directly proportional to voltage and is inversely proportional to resistance. The higher the resistance, the lesser the current. The higher the voltage, the higher the current. So this is what it means. So that's basically what Ohm's law is stating. Quantity, current, voltage, symbol, unit of measurements, and unit of abbreviation on this side here. Okay, let's look at Ohm's law. Ohm's law defines the relationship between voltage, current, and resistance in an electrical circuit, stating that the voltage across a semiconductor is directly proportional to the current flowing through it. Voltage equals to current times resistance, provided temperature remains constant, because temperature is one of the very important factors in electrical conductivity. When you increase or decrease the temperature, it also affects the resistance and the conductivity of the circuit. So temperature, that Ohm's law is satisfied if the temperature is constant. It is a fundamental concept used to calculate how these three variables operate. So if you want to calculate voltage from Ohm's law, basically in words we can say that the amount of current flowing through a circuit is directly proportional to the voltage and inversely proportional to the resistance of the circuit. So that's the Ohm's law triangle there. First one, if you want to calculate the voltage, you circle the voltage, you are left with current and resistance. So voltage equals to current and resistance. If you want to calculate current, circle the current, and you are left with V on R. If you want to calculate resistance, circle the resistance, and you are left with V on I. So that's how you use the Ohm's law. Or you can use it for any three variable formula. You can just Ohm's law, power and energy. Now we can also relate power and energy into Ohm's law, because power is equals to current times voltage, and energy is equals to power times time. So we can relate current, resistance, voltage, power, and energy. So Ohm's law defines the relationship between voltage, current, and resistance. Power is equals to IR, is the rate at which energy is consumed, measured in watts. Energy, okay, E is equals to power times time, is the total power used over time, usually measured in joules or kilowatt hour. So that's the amount of energy. These principles are foundational for circuit analysis. So once you understand this Ohm's law, relate power, current, voltage, energy, and resistance, this forms the basis of circuit analysis. So make sure you draw this circle here and understand how you can use it and the interpretation of this circle here. I'll go through some of one of the example here. Let's say example, we try to use the Ohm's law here. We have a circuit here, it's a DC circuit. If you see a battery there, that's 50 volts, it's a DC circuit. We have a 10 ohm resistor, and that circle and A in there is ammeter there. So that ammeter is measuring the current in the circuit. It's not giving any value of the current, so we can use Ohm's law to find the current there. Using Ohm's law, current is equal to voltage divided by resistance, so 50 divided by 10 ohms is 5 amps. So that ammeter there connected to the 10 ohm resistor will be reading the 5 amps on the ammeter. So also, if you want to measure current in a circuit, you connect the ammeter or current measuring device in series with the circuit. For voltage, you will have to connect that in parallel with the circuit. And then the Ohm's law is on this side here. We use the Ohm's law here. Okay, that's another example here. So it should be example 1 and 2, but anyway, we do make mistakes, so it's good to make mistakes, but minor mistakes. Okay, let's look at the circuit here. We have current through the circuit. It's a series circuit, single pathway. We have current is 5 amps. The resistance of the circuit is 200 ohms, and we don't know how many voltage DC supply going through the circuit. So if you use the Ohm's law, voltage equals to current times resistance. So if you multiply 5 amps by 200, we are going to get 1000. So you can say 1 kV. That's the same thing. So using the Ohm's law here. So okay, now let's we have discussed a lot about electricity. Let's look at the history of electricity. Normally in some lessons and some the way they conduct these classes, they usually start with history, but I decided to put history in the middle of the class just to the reason why is let's understand what is electricity first, and later we will try to read about know about the history of electricity. So that's the reason why I'm putting that the history of electricity. I'm slotting it towards the middle of the class. So basically, let's look at the history of electricity. Electricity was discovered, not invented. So electricity was already present, like in the form of lightning or whatever. Electricity is present, so they just discovered that electricity. So it's not invented, evolving from ancient observation of static to modern power systems. Key milestones include tales of Miletus noting static electricity. It's about 600 BC before Christ. Franklin linking lightning to electricity in 1752. Alexander Volta creating the first battery in 1800, and Michael Faraday developing generators in 1831. Edison and Tesla later revolutionized the world with practical DC and AC system. That's from 1880 to 18. Okay, let's look at the historical milestone in electricity. Ancient observation. So about 600 BC, Greek philosopher Thales of Miletus observed that rubbing amber electron attracted light object, documenting static electricity. So charges that are at rest are called static electricity. Static charges, they are at rest. They say static electricity. These are a topic of its own. So static electricity was discovered in 600 BC, and then 17th to 18th century foundation. William Gilbert in the year 1600 coined electric cars, while Benjamin Franklin's 1750 kite experiment proving lightning was electrical. So these are some of the discoveries. They discovered lightning. It's a form of electricity, natural electricity, by Benjamin Franklin. 19th century breakthrough in the 1800. Alexander Volta created the first electric battery. So that's why the unit of voltage is named after him. Voltage, generating a consistent current. In 1821, Michael Faraday discovered electromagnetic rotation, leading to the first electric motor. So that's the discovery of electromagnetic induction principle. Now the capacitor, the unit of capacitor, is named after Michael Faraday. So Michael Faraday invented the electric generator, paving the way for large-scale power production. So because of this electromagnetic induction, now we can have AC power generation, motor generator. They all work on the principle of Michael Faraday. James Clerk Maxwell formulated the theory of electromagnetism in the 18th. Okay, let's look at the 18th century. Commercialization in the 1879, Thomas Edison developed the practical incandescent light bulb. In 1882, Edison opened the first commercial power plant, Pell Street Station, the name of the power plant. In 1890, Nikola Tesla championed alternating current AC, which won the war of current against Edison direct current to allow long distance power distribution. So AC current was discovered by Tesla. Prior to that, DC was the only power source that they used, but after the invention, AC is invented by Nikola Tesla, so that's where the AC power comes in, so we can have AC power generation and long distance power distribution because of Tesla's invention of AC current. In the 20th century onwards, electricity became essential for modern life, including radio. In the 1900s, advanced electronics and the current shift towards renewable energy sources. So this is let's look at what is an electrical circuit. An electrical circuit is a closed, unbroken loop of conductive materials or conductor that allow electric charge electrons to flow, driven by a voltage source or force, electromotive force. It typically consists of a power source, which is the battery, or it can be an AC source, generator, conductor or wires, a load, okay, and a switch. So these are the basic components of a circuit. We have power source, it can be AC or DC source. We have the conductor where the current will flow through, and we have a load where it will power, like light or anything that consumes electricity is a load. And for the circuit to be controlled, that's when we have switch. So switch is like a controller. Circuit can be arranged in series, okay, that's when we have one pathway for the circuit for current to flow, or when you have multiple pathway, then that circuit is a parallel circuit. So these are the two types of circuit in terms of their okay. These are the major components of a electrical circuit. Power source provides a voltage pushed to move electrons, such as a battery or wall outlet. It can be AC or DC power source. We must have a conductor, which is a pathway where the current will travel around the circuit. So material, usually copper wire, that allows electricity to flow. So gold and silver, they are the most best conductor, but because of their rare abundance in nature and their high economic value and all this, we are not using them as electrical conductors, and they are using copper and aluminum. But the good conductive materials are silver and gold. Okay, load, the component consuming power, such as light bulb, motor or heater. So anything that consumes power in a circuit is a load, or they say electrical load. Okay, switch is like a control in a circuit. We cannot continue to allow power to run in a circuit to continue light up the light or run the motor. We have to have some sort of control. That's when a switch comes in. A switch is sort of a control device that open and close the circuit to allow current to flow through, or open and open the circuit so current to flow through. So that's what a switch does in a circuit. So a component that controls the electricity by opening, stopping, or closing, starting the flow. So these are the basic four components of a circuit. Any complex circuit builds on from this one here. Any complex circuit, you can break all the components and classify into these four basic components. So we have power source, conductor, load, and switch. Let's look at the next slide. It doesn't matter, a circuit can be more complex, but the components in a circuit will be classified into these four. Okay, types of electrical circuit. These are some of the features here. We have series circuit on the first circuit up there, one pathway, two lights connected to the battery, and then parallel circuit, two different pathways. The first branch up there and the second branch is where the two lights are connected, but we have two pathways up there. Open circuit, when the switch is open. I don't know why the bulb is still glowing there, but it's an open circuit. I think the bulb does not glow, it's just because it's white, so it seems like it's glowing, but it's not actually glowing because it's an open circuit. We have closed circuit here, that's when the bulb glows. Short circuit, when there is a fault condition, so that's when we have a short circuit. Main types of electrical circuit, series circuit, yeah, everything is connected in series, and that also bring us to the measurements, basic measurements here. If you want to measure current in a series circuit, you connect the ammeter in series with the circuit. Ammeter is current in a circuit is measured using an ammeter, and the way you connect the ammeter, it has to be in series with the circuit components to measure the current across there. and it's opposite to voltmeter. Voltmeter, if you want to measure the voltage in a circuit, you connect it in parallel with the components to measure the voltage across the components. Why? Because when you compare the circuit later, you will see that in series circuit the current is constant while voltage vary from load to load. In parallel circuit, the voltage is constant across all the loads connected in parallel, but the current differs in each of the branches. Combination circuit, when you have a series parallel arrangement, we do have complex circuit when series and parallel circuits are put together, but the same principle apply. If you want to measure voltage, connect the voltage in parallel with the load. If you want to measure current, connect it in series with the load to measure the current across that. These are the comparison. We have diagrams for series circuit. Current flows through the series circuit is constant. Same current flows through all components. Voltage in a series circuit, voltage is set across the components. So if you have 3 lights up there, the voltage is equally, it's not equally, but it divides according to the value of the resistance or the load capacity of the 3 light in there. So voltage is divided. Application, flashlights, Christmas lights, and all this, they are all series circuit. Parallel circuit, we have current splits through multiple branches. The voltage is the same in all the parallel branches. The application of this parallel circuit is ohm wiring appliances. Of course, all the ohm wiring plus most of the industrial wiring are all parallel circuit because the voltage has to be constant in all the circuits. So in parallel circuit, the voltage is constant, except the current will differ. The amount of current going to a particular load like light or fan or whatever it is, it depends on the capacity of the load. So all domestic circuit and industrial circuit, they are all parallel circuit, meaning voltage is the same. Almost all, not all of them, but some are series circuit, like sensor circuit, they are series circuit. Okay, combinational circuit, that's when you have both series and parallel in one circuit. It obeys the same principle. The part that we have a series circuit obeys series principle. The part that is parallel obeys the parallel circuit. So voltage is same, current is different in all parallel circuits. Current is constant and voltage is different for all loads across a series circuit. So application of series parallel, we have computer, electronics, and complex circuit. That's when all the loads and components are connected in series and parallel. This is a series circuit, one pathway. We have battery, bulb, resistor, motor. They are all connected to the battery, so one pathway. If anything happens in this path or circuit, everything stops working because there is one pathway where current flows through. It is a parallel circuit. All these lights here are connected parallel to the battery here, also the voltmeter here. So if one path goes off, the other 2 lights will go on, but the other 1 light will go off. The other 2 will still be working. If 2 goes off, 1 will still be working. Unless if 3 of them is broken, 3 parts are broken, then all of them will go off. But if 1 or 2 parts are broken, the other 1 will still be working. That's parallel circuit, but the voltage is constant across these all 3 branches. Current differ based on the load capacity of each of the load, and then the voltmeter is connected in parallel with the lights or the this is a series parallel circuit. When you look at lamp 1 and lamp 2, they are connected in series, and then when you see lamp 1 and then that 6 ohm resistor there, they are in parallel. So it's a combination of series parallel. But later when you look at circuit analysis, how to combine resistor in a series and parallel and all this, you will see how we can reduce this whole circuit into one resistor, so we can find out the total current, the voltage, power, energy, and all these things. But the basic concept now is, the series circuit, one path, parallel circuit, multiple branches. Series circuit, when one component goes off or the circuit breaks, everything stops. While for parallel, if one branch stops open or faulty, the other branch is still working. Current is constant in a series circuit, voltage is constant in a parallel circuit. Voltmeter is connected in parallel with the component in parallel circuit to measure voltage. Ammeter is connected in series with component to measure current. Open circuit, when the example of open circuit, when the switch is open. This is a classic example of a open circuit. It's a series circuit, so the light will not come on because the current will not flow. In a circuit, there must always be a complete path for the current to return back to the source. If it does not return to the source, that's when the circuit is incomplete. So if there is any light or load or whatever, it will not be powered because the current has to make. There's a closed circuit. That's when the current flows around and then the light comes on. And then we have short circuit. If there is a burning wire or if there is a foreign element in contact with the circuit, that's when it creates a short. So the current will take a short path back to the source. So that's when we have short circuit. So the bulb will go off and there will be a short circuit. Mostly short circuit, you must understand the basic definition of a short circuit. That will help you to understand a complex problem. Short circuit is when there is a fault in a circuit and the current takes a shortest pathway to the source, or a pathway that does not have any load. So the current will take a short pathway, bypassing all the loads and back to the source in short circuit condition. Okay, circuit can be classified as DC and AC circuit. Basically, DC circuit, we have cells of battery. Solar power is also a DC source. The difference between DC and AC is DC travels in one direction, does not change any direction, and it's constant. When you look at the graph down there, it's constant. And once the load uses the power in the circuit, the value of the DC drops. Like battery, when you buy it from the store, you use it for some time, the voltage level drops down. So that's DC. For AC, the voltage level fluctuate and oscillate or alternate or changes direction from high to low, high to low, high to low. So that's what it is, changes direction. And when it changes direction, there's a time where frequency comes into play. So DC does not have frequency. You cannot say DC voltage is that much frequency. No, DC does not have any frequency. Only AC or alternating current has a frequency. Frequency is one of the features of alternating current. And later, when you look at the AC current, you would see what are the features or properties of AC current, like amplitude, peak-to-peak value, frequency, what is a duty cycle and what is a frequency, and what is a period, peak-to-peak value, all these things. So basically, a AC circuit as a AC source, like generator is AC source. The current flow changes direction, and when it changes direction, it oscillates and it has frequency. DC travels in one direction and it's constant. Once the load consumes the power from the DC, the level of the power source drops. Okay, let's look at the different types of circuit. Series, same everywhere, current is same, voltage is divided. When there is a defect in the circuit, all devices stop. Common application, sensor, battery packs, and all this. Solar and car battery and all this, they are all series circuit. They use series circuit. Like in some application, if you want to increase a voltage level of in a solar system, or I mean photovoltaic system, whatever, they connect batteries in series. So as solar panels, they connect in series, so the voltage adds up. Parallel circuit, the current divided in the voltage is same in parallel circuit. When there is a fault in one branch, others keep working. Application, it's used in home wiring or industrial application. Series parallel, it's a mixed circuit, both parallel and series circuit. The voltage is controlled. Device failure, partial effect, meaning some parts that is the series circuit, they will go off. Some of the application is in electronics and printed circuit boards or PCBs. Open current, open circuit, that means there is no current in the circuit. The circuit is not complete, so there is no current flow. Current will always make its way back to the source. If there is an open circuit, current will not flow. Okay, so if this circuit is closed, there is guarantee that the current will come back to the source, so the current will flow. But if there is an open circuit, current will not flow in a circuit. No voltage draw, no operation, switch off condition. Closed circuit, the current will flow, proper distribution of voltage, everything works normally, and for application everyday use, closed circuit, like we switch on the switch and power comes on, light comes on, fan comes on. Short current is extremely high. In a short circuit condition, the current is extremely high. So that's one of the reasons why in any power system or electrical system that they design, they will have to test to see that if there is a short circuit, the amount of high current that will flow through the circuit has to be sustained by the size of the conductor that they use. So in a short circuit condition, the current in the circuit is extremely high because it takes the low resistance and shortest way back to the source. So in that way, if there is no resistance, that means high current. So that's one of the effect of short circuit. Very high current flowing back to the source in less resistant pathway or short way back to the short pathway or back to the source. Voltage collapses, damage is in the case of short circuit devices, they damage or they go faulty. Common application or some of the examples of short circuit fault condition, like in the house when there is overloading, the circuit breaker trips. If there is overcurrent going through a device, then one component bend, that's when we have short circuit, so the device does not work anymore. So in any fault condition where there is overloading or faulty component all this, that's when we have short circuit. Real world electrical circuit facts: over 90% of residential electrical systems are parallel circuits. Most electrical fires occur due to short circuits or overloaded circuit. Modern devices rely on series parallel PCB circuits for efficiency and power control. So PCB, printed circuit board. So most of the circuits in the industry and at home and commercial, they are all parallel circuit. That's one of the real world circuit facts. Circuit during most of the building catch fire and all this because the power supply to that building is low and they are adding a lot of loads onto that power. So that's why the circuit overloads, so it bends. So most electrical fire occur due to short circuits or overload. So these are the two causes of building catching flames. Mostly in the country, we have seen a lot of buildings going down in flames due to electrical forces because of short circuit and overloading. Okay, short circuit happens sometimes when there is aging equipment in the circuit, like on the line when the transformer blows, it's a short circuit, it's a fault on the circuit. Or in a system, any equipment or any component of the circuit is sitting there for a long time, it gets faulty and then it blows off. That's when we have a short circuit condition. All of the modern devices like computer, phone and all this, they rely on series parallel arrangement. So mobile computer, all the control circuit and all this, it's both series and parallel circuit. Some importance of electrical protection. Safety is very important. We must always prevent electrical fires. circuit breakers and circuit protective components like circuit breaker and fuse must be also always used in a circuit to prevent the circuit. In the case of fault or whatever, this protective device will protect your circuit. Later you will know what is a fuse and circuit breaker. Avoid electrical shock. You must wear PPE or safe personal protective equipment. Especially for computers on this, you can use sets protector or the UPS. They say UPS in official this thing. You will see a small battery like box sitting there, black box. It protects computer and everything from sets. Sometimes when the power goes off, everything will go off. So that UPS stores power there, and then when the power goes off, it temporarily powers the computer, so you can save everything and shut down. Grounding of a electrical system is necessary, because if anything happens, if there is a fault, the current quickly takes the ground part, the ground wire, and go back to the ground. So grounding must be properly done in any circuit to ensure safety. These are some of the practical applications of different types of electric circuit. We have home wiring. Home wiring are all parallel circuits. Electronic devices, analog and digital circuits. We have automotive circuit. They are series and parallel circuits. Renewable energy like solar and all this, they are all DC circuit. Battery and solar power, they are DC circuit. We have robotics or embedded system. These embedded system, they usually they use transistors and ICs and processors. They are like mini microcomputer. There's software and hardware and all these things to control this operation of this. So this is an embedded system like robotics and all this. Then we have industrial control circuits, like complex operations in the manufacturing industry, mining, all these controlling process of manufacturing food, or process of processing gold, or process of anything that is undergoing a process in the factory. Then they use control circuit to control all the process, motor and all the equipment that are running the process. So basically this is some of the application of the circuit. I think the lesson continues. We will do another video and upload maybe later on to continue on that, but this brings us to the end of the first video here. Some of the next videos that we will be doing, we will be emphasizing on the circuit analysis, how to calculate series, parallel circuit, energy, power, and all these things using Ohm's law, energy and power formulas. Thank you.